Hello everybody, and welcome to section 8.6 on power series. We are on page 123 of the workbook. So in section 8.5, in the previous section, you learned about Taylor polynomials and Taylor series. And in that section, you learned how you can use a polynomial, and if you keep adding terms to that polynomial and keep going forever, how you can use series to represent a function. In this section on power series, we would like to learn more about for what values of x you can do this. For what values of x you can really write and approximate a function as a series. So for example, you saw how you can write e to the x as infinite polynomial, as a series that keeps going on and on and on. But the question is, does it really work for every value that you could plug in for x? So those are the types of questions that we are interested in examining in this section. And for those function values that you can use a series, the question is, how many terms do you need to have a workable approximation? That's the second question. And then a third question that we want to investigate is, you saw that finding Taylor polynomials was actually a lot of work. You had to take a lot of derivatives. It was a lot of work to come up with a series. And so in this section, we are going to learn some methods where we can build new series from old ones. And we'll see a bunch of methods that are going to help us with that. But to get us started, let's look at example 1. So here we have a Maclaurin series that we already saw in example 1 on page 114. And if you remember, a Maclaurin series is a Taylor series that is expanded around a equals 0. That's really it. It's a special type of Taylor series. And so here we have the Maclaurin series p of x equals the sum where n goes from 0 to infinity of 2 to the n over n factorial x to the n. We'd like to learn more about this series. In particular, we'd like to know for what values of x we can use this series to approximate e to the 2x. So like we often do with new examples, let's write out the first few terms of this series. Let's write out the first partial sums. So we want to find p2 of x, p3 of x, and p4 of x. And p2 of x, that is the second degree Taylor polynomial. So we need the constant term, the linear term, and the second degree term, the quadratic term. So when n is equal to 0, we have 2 to the 0 divided by 0 factorial times x to the 0. And when n is equal to 1, we get 2 to the 1 over 1 factorial x to the 1. And we need one more term. That gives us 2 squared over 2 factorial times x squared. And here you may look at that and say, hey, wait a minute, what is 0 factorial? That is a very good question, and it's worth noting that up here, 0 factorial is defined to be equal to 1. So this is the definitions that mathematicians made pretty much to make math work. So please remember that 0 factorial is equal to 1 whenever you see it. So let's simplify. 2 to the 0 is 1. 0 factorial is 1, x to the 0 is 1, so our first term is 1. And then we have 2 over 1 factorial, that is 2, x to the 1 is x, and then we have 2 squared is 4, divided by 2 is 2, x squared. So this is our second degree Taylor polynomial. Let's write down one more. Actually, we want two more. So p3 of x starts out the same way. We have 1 plus, I'm going to write it as 2 over 1 factorial x plus 2 squared over 2 factorial x squared, and then plus 2 cubed over 3 factorial x cubed. That's our third degree Taylor polynomial. And we can simplify that just a tad as 1 plus 2x plus, 2x squared plus 8 over 3 factorial. I'm just going to write it as 3 factorial x cubed. And for P4, it starts out the same way. 2 squared over 2 factorial x squared plus 2 cubed over 3 factorial x cubed plus one more term, 2 to the 4th over 3 factorial x to the 4th. Oh, sorry, gotta fix that. That is a 4 factorial in the denominator. 2 to the 4th over 4 factorial x to the 4th. So that is 1 plus 2x plus 2x squared plus 8 over 3 factorial x cubed plus 16 over 4 factorial x to the 4th. And if you like, you could simplify this a little bit more. But so these are the first 3 Taylor polynomials. So those are Taylor polynomials. For the function that we'd like to approximate, f of x is equal to e to the 2x. And the graphs right here, so we have 4 graphs, they illustrate how good these approximations are. So the dotted line always shows the original function. I'm going to draw it in green. So right here, this is the original function. That is f of x equals e to the 2x. And then in red, you can see the approximating function. The second degree Taylor polynomial in our first picture, you see that we have a quadratic approximating it, and it's pretty good about x equals 0. But the further you get away from 0, you can see gaps right here. So the approximation is not that good the further you get away from x equals 0. Moving on to the third degree Taylor polynomial, we can see that we have a little bit better of an approximation. So it lasts further away from x equals 0. So it's pretty good, like in this range. But then it starts also, we can see a gap. And with the fourth degree Taylor polynomial, we have an even better approximation, and the gap appears further away from 0. And when you're looking at the picture for the fifth degree Taylor polynomial that we didn't write down, but we have it graphed right here, you can hardly see a difference between the function e to the 2x and the Taylor polynomial of fifth degree. So that's already a pretty good approximation all the way from -1 to 1. Seems to be pretty good. But the question is, that's an interesting question, is this gonna work for any value of x? What if we kept going out further and further? And I go out, I don't know, to plus 10 or to minus 10. Is my fifth degree Taylor polynomial still good? Probably not. But what about my sixth degree, seventh degree, eighth degree? Will there be enough terms so that I still have a good approximation when I go very far away from the point where we expanded our polynomial about? So fortunately, there is a systematic way to figure this out, and we're going to illustrate it in part B. We want